Perfect.
Okay.
It's great pleasure to have Dan, who will be telling about two-or infinity.
Okay, great. Thanks a lot for the invitation. It's been a while since I've given a Zoominar, so it's great. I want to talk today about this two-or infinity phenomena. Sorry, my toddler is running around, so let me actually get slightly out of here.
Take it out. Better.
Okay. Okay. So hopefully you can hear me okay. Anyways, yeah, so it's great to be here. So I'm going to talk about this two-or infinity business. I want to note, especially the middle part of the talk is technical, and I would really like people to understand. So please stop me if you have any questions. That's another reason I put the slides in advance on the internet so that you can follow. Okay, so anyways, let's get into it. Oh, there's also a strange, well, okay, I guess we'll just do it like this. Okay, so I want to start with some notation. I'm talking about.
It's a little hard to read though. Can we try to do
Oh,
a
is it?
simple switch?
Yeah, I actually like it better in this method. Is this, can you see the whole screen? Can you see the whole screen if I do it this way?
Yes, we can see the whole screen. Yes.
Okay, great.
Yeah,
And
this is great.
You can hear me okay?
Yes.
Okay. Sorry for the technical hiccups. Okay, so we're starting with, I want to just start by reviewing some notation. So we have a closed oriented three-manifold. It has a contact form. Okay, I think we know what this is. That has an associated Reeb vector field. I mean, I'm not sure the level of specialization of the audience, so maybe I'll just quickly say, it's in the kernel of d lambda, and it's normalized to have length 1. The dynamics of the Reeb vector field are of a lot of interest. We're particularly interested in the periodic orbits, which are called the Reeb orbits. And we're also interested in the context structure, which is the kernel of this thing. Okay, so just to check one more time, people can actually see the slides and everything's okay?
Yeah, good.
Okay, great. Okay, so I now want to give a series of, I want to tell a kind of story, and I want to use some primary sources in the sense that I want to actually use like the original papers, partly for fun. Okay, so there's a number of questions and conjectures about Reeb orbits, and they've interested me for a long time. And so here's what we're going to be talking about. Okay, so the first comes from this classic paper. I think it's from 2001. So it's all about Reeb dynamics on the three-sphere. And there proves a lot of stuff, but it has the following conjecture. Okay, so let's read it. So it says that a tight Reeb flow on the three-sphere has either two or infinitely many periodic orbits. And so HWZ, Hofer, Wysocki, and Zender, they prove it in two cases, which is relevant to us. The first is they prove it in the generic case. Okay, so in the paper, they prove it in the generic case, and they also prove it in the convex or more generally the dynamically convex case. So we'll return to actually both of those points in a minute. Let me just say again for non-specialists, also just notation, when I put things in parentheses here, I guess I'm hoping that both people who are quite familiar with these kind of questions and others will get something out of this talk. So when I put something in parentheses, it's sort of meant for a non-specialist or something. So anyway, so tight just means in this case that the context structure is the standard context structure, that you would get just by taking the standard primitive of the symplectic form and restricting it to the boundary of the standard law. So okay, so if I get that context structure, conjecture is that I have two or infinitely many orbits. Okay, so that's an interesting conjecture. Actually, I want to say some further reasons why I find this interesting. So this is a problem that actually interested me ever since I was a PhD student. There's maybe two reasons why I was interested. The first reason is that, I just said that HWZ proved this tour infinity result in the generic case, but it was curious to me already as a PhD student why, should the generic case actually be representative? So here's some finite dimensional problem. You can argue whether you think it's a reasonable analogy or not. But so on the two-sphere, on the two torus, there are functions with 3 critical points. But if you want a Morse function, it has to have at least 4. As is well known. In other words, in this particular case, if you're interested in questions about the number of critical points, the generic case is not representative. It doesn't seem improbable that there's some contact form with exactly 7 Reeb orbits lurking in away from the generic case. Okay. The second reason I found this interesting is, how are we even going to study these kind of questions without requiring non-degeneracy? So again, there's something that specialists can take out of this, and there's something that non-specialists can take out of this. But at just a basic level, I probably want to use some kind of floor theory, and I probably want to assume that the contact form is non-degenerate. So again, I talk about non-degeneracy a little bit later for non-specialists, but think of non-degeneracy as analogous to the Morse case. So if we're trying to work out of the Morse case, how are we going to develop good tools to actually do this? So those were 2 reasons that I found this particular question interesting. I have more questions, but let me just stop for a second to see if there are any questions anybody has or any technical glitches with the slides or anything. Okay, so everybody understands the notation, everybody can hear, etc. Great. Okay, so that's one question. Okay, here's another question, and again, I sort of having some fun with the primary sources here. So here's a survey article by Hutchings from 2000. I think it was published in 2010 or something like this. It's about Taugs's proof of the Weinstein conjecture. So again, for non-specialists, the Weinstein conjecture is the statement that there's at least one of these periodic orbits, these Reeb orbits. So that's already, generated quite a lot of very interesting mathematics. But let's say we know that that's true, and Michael has written a beautiful survey article about the proof. And if you get to the end of the survey article, it contains the following interesting question. So Hutchings asks, let's say that my manifold is not the sphere or a lens space. Does every contact form have infinitely many Reeb orbits? So interesting question. Okay, and here's more interesting primary sources. So this one was pretty fun. Okay, so what's this? So this is the ICM address of Anisoff. It goes for about 5 pages. I've only put the first couple paragraphs. It's called geodesics in Finsler geometry. For time reasons, we're not going to say much about Finsler geometry, but I just want to kind of quote Anisoff directly. I did my best to translate this with the help of Google Scholar and with the help of a native speaking friend. So there is this Finslerian geometry. Maybe we won't take time to define it, but it's interesting to see what Anisoff writes about why he's actually interested in it. So, if you look at the first paragraph, so Finslerian geometry is a generalization of Riemannian geometry, which, as we'll see later in the talk, is quite natural for us as contact and symplectic geometers. So, but what Anisoff says is he says it's interesting to think about Riemannian geometry in concert with Finslerian geometry, because then one can find problems in the Riemannian setting, which you can better understand which theorems in the Riemannian setting come from their variational nature alone, rather than some specific Riemannian features. Okay, and so then he uses the problem of closed geodesics on a sphere, and he compares the results of Lustrom-Schillerman to the Finsler case. So, eventually one finds that in the Riemannian case, if you're looking at the number of closed geodesics on the two-sphere, what one finds that in the Riemannian case, there are infinitely many. On the other hand, as Anosov points out, in the Finsler case, there's actually an example due to Katak with two closed geodesics. Again, maybe for some of us, this is kind of well known. Anyways, then he makes an interesting comment. So he says, maybe the number of closed geodesics that can be expected on the basis of variational considerations at all alone is very small and perhaps unimprovable. Okay, so anyways, so there's not even a concrete question here, but interesting thoughts from Anosov. In the Finsler community, there is a kind of concrete question about closed geodesics on in the Finsler setting, which is clearly related to what Anosov writes, and so actually this has been asked by several authors over the last 20 years or so. So the question is, does every Finsler metric on the two-sphere have either two or infinitely many prime closed geodesics? So let me just say with prime again, I just mean, so of course, once you have a closed geodesic, you can go around it more times, then you get, technically speaking, a different closed geodesic. So this is really just demanding that the geodesics are geometrically distinct. Yeah, so okay, so here's some interesting questions. So these are some questions that have interested me for a long time. Any questions about any of that or comments? Okay. So now I want to tell you what we know about these kind of things. So there's actually a lot that is known with contributions due to many people, but I just want to say sort of the state of the art and give you some sense of the history. So, okay, so in this entire talk, we're always talking about just closed, connected three manifolds with a contact form, oriented, say, by the contact. Okay, so what do we now know? Well, first of all, there's always at least two simple Reeb orbits. So again, this word simple, I'm just putting that so that we don't have to worry about this issue of multiply covered orbits. I mean, technically, once I have one Reeb orbit, if I take its multiple covers, I get infinitely many. Okay, so that's good to know. Okay, moreover, if there are exactly two orbits, then you do learn that the manifold is a lens space, and you learn more things too. I mean, you actually learn quite a lot about the context structure. So one way to say it is that not only is the manifold a lens space, but the context structure is the standard one. Okay, we also know in the non-degenerate case, there's always either two or infinitely many Reeb orbits. So certainly getting pretty close to satisfactory answers to these questions. Okay, right. So here's another remark about non-degeneracy. For the non-specialist, I don't want to actually define it. I mean, you can define it just by demanding that one is not an eigenvalue of the linearized return map around all the Reeb orbits, but I don't want to put it on the slide. So if you're not a specialist, you can just think of it as analogous to the Morse case. And a very important point, which will certainly come up in the proof that I'm going to explain in the middle part of the talk, is that this holds generically. Okay. And there's a lot of other stuff, but I wanted to keep the slide relatively readable. But I want to point you to our archive preprint where we try pretty hard to give everyone the credit that they're due. But anyways, these are sort of what I would call the state-of-the-art results. Okay, and okay, so here's the main theorem that I want to talk about today. All right, so the point of the theorem is that it does not require non-degeneracy, but there is something required, which is that you require that the Chern class of the context structure is torsion. Okay. So you get a lot of corollaries of this. So first of all, remember the very first conjecture, this conjecture of HWZ from their beautiful paper. I mean, it certainly implies that. So why does it imply that? Well, we just need to check that the Chern class is torsion, but in the case of HWZ's conjecture, the three-manifold is the three-sphere. So certainly the Chern class of the context structure is torsion. So, and then not only do you learn that, but you learn something else interesting. So remember on a previous slide, I said that if there's exactly two orbits, then the context structure is standard. So you also learn that, on the three-sphere, say, if you have the different over-twisted context structures, again, if you're, not aware of what I'm saying, I don't want it to be sidetracked. It's not central to the talk, but for the specialists, if you have the over-twisted context structures, the theorem combined with the previous theorem I told you about the case of two orbits is telling you that they actually have infinitely many orbits. Okay, you also learn this two or infinity conjecture for Finsler geodesics. Again, I don't want to belabor this point, but that's just because there's a contact form, let's say on the unit tangent bundle, such that the Reeb orbits project to closed geodesics. So there's a kind of beautiful story about this. And anyways, in the case of the two-sphere, you're just looking at RP3. So you can, and in fact, you can actually prove, these other kind of classic theorems about closed geodesics on surfaces this way. I mean, in all the other cases, you get infinitely many, and you can also see that from this point of view, because it turns out that the context structure is always torsion. Okay, so as for now, remember there was also this question of Hutchings, which said if you're, I'll just remind you what it is, says that if you're not a lens space, you always have infinitely many orbits. And so now we also know that, at least in the case where the context structure is torsion, and that happens quite a lot. I mean, in a certain sense, most three manifolds are rational homology spheres, and that condition is always going to hold, obviously. But of course, it doesn't fully answer it. Okay, so to sum up, if you take all the two or infinity questions I mentioned, we now understand all of them, except for the case of degenerate contact forms whose Chern class is not torsion. And you would certainly guess, given everything that I've said so far, that there are infinitely many in that case. So yeah, so personally, I'm pretty happy about this because I don't know, I was a PhD student, I don't know, 10, 12 years ago, quite interested, and it seems like we're really starting to get a handle on these kind of questions as a research community. Okay, so so that's sort of the end of the first part of the talk. Are there any questions about the notation or anything? Any questions about any of this or the results? And okay, please stop me if there's any technical problems. You can see the slides and everything. Okay, so I can't really hear anyone. So people are actually here, right? Can someone confirm?
Yeah, we are here.
Yes, we are here.
You're
It's going
fabulously
great.
clear.
Okay, good.
Yes, you're fabulously clear. That's the
I have it on full screen, so I can't see the chat, and I've already had some technical difficulties, so I don't want to be just talking to. I'm right outside my bird feeder, and I don't want to be talking to the birds alone. Okay, right. Okay, so yeah. So now, for most of the remainder of the talk, I want to tell you how to actually prove this theorem. So again, the theorem says that you can actually deal with the degenerate case, but at the expense that you have to have to assume that the context structure is torsion. And it's a long and technical proof. So I don't think I will be able to explain, the entire proof, but I want to tell you about the key ideas and give you a sense of how it goes. Okay. All right. So let's first try to clarify the basic strategy. Okay, so to put this in some context.
Hello, sorry. Can I ask a question?
Yeah, please ask questions. Great.
What is known when the Chern class is not torsion? I just didn't get
Right.
it.
Well, so
Two
I'll go
slides
back
ago.
even because I made these slides. It's great to use them. So maybe I went back too far. Okay. So here's the state of the art. Right. So the third bullet point is pretty much the state of the art. Namely, in the non-degenerate case, there are two or infinitely many simple Reeb orbits. So in the non-torsion case, that would be the state of the art. But let me remind you of the second bullet point as well. The second bullet point says that when there are exactly two orbits, the manifold is a lens space. So if you combine those two bullet points, the non-torsion case is, so if the context structure is not torsion, then the manifold cannot be a lens space, right? Because if it was a lens space, just for cohomological reasons, the Chern class of the context structure would have to be torsion. So if you combine the second and third bullet points, you learn that the state of the art in the non-torsion case is that there are always infinitely many orbits if the contact form is non-degenerate. In the degenerate case, as far as I know, nothing's known. Does that answer your question?
Thank you.
Yeah, great.
Yes.
And yeah, please do ask questions. Yeah, I'm much happier if people ask questions than if I get through the slides. Okay. Any more questions? Okay. So yeah, so how are we going to prove this? Well, yeah, so maybe I want to recall some of the things I already said in the introduction. Maybe the first thing I said was that, in the degenerate case, how are you even going to get started? Because maybe you want to use some kind of floor theory or something like that, but it's not even defined without this non-degeneracy condition. Another thing I said on the first slide, which was, I said we'd return to later, is that HWZ themselves actually did prove something in a degenerate case, because they proved that in the convex case, that there is two or infinitely many orbits. If you remember from that very first slide, where I stated HWZ's conjecture, that they state that they themselves proved it, in the convex case and in the generic. So in the convex case, they don't need non-degeneracy. And so the first place to start is to understand how HWZ actually do this. And they do this by finding a global surface of the section. So that, that's very motivational for our approach to the problem as well. Okay, so what is a global surface of section? Again, I assume the audience breaks up into some specialists and non-specialists. So here I'm just going to talk about an annular global surface of section. So maybe it's best just to show a picture. I feel like you learn a lot just by looking at a picture. So I'm looking for a compact annulus S. Okay, I mean, this is going to be, like I said, an annular global surface of section. You could look for more general ones, but not what we want to do. Okay, so basically S is going to be embedded in the three-manifold. It actually could be immersed at the boundary, and that's actually something we need to consider in what we're doing. But the point is that I want to be able to do a dimensional reduction. So it should be transverse to the Reeb vector field, and every flow line should hit it both forwards and backwards in time. And so the real point is, maybe you can even see the little arrow, this so-called Poincare return map, where I start with a point X, and then I follow the Reeb vector field, see where it hits the surface of section again, and I get a new point P. Okay, so in other words, if I actually have this, I get a map from the interior of this annulus to itself. You get it has to preserve the restriction of d lambda because it's transverse to the Reeb vector field. And so you get this kind of dimensional reduction where instead of studying the dynamics of the three-dimensional flow, instead you can study the discrete dynamics of this area preserving map of the open annulus. And if you're just interested in the Reeb orbits, instead you're interested in the periodic points of this map. Okay, so that's cool. And then there's a famous theorem, now several decades old, says that if I have an area preserving homeomorphism of an open annulus and it has at least one periodic point, then it has infinitely many. Okay, so if I actually had an area preserving, if I had a global surface of section that's an annulus like this would now be like a proof of our theorem, because Franks is not requiring any non-degeneracy or anything like that. And I mean, right, so basically, if I had a global surface of section, I've reduced this 2 or infinity result to a 0 or infinity result for annuli as proven by Franks, right? So, so just going back to the picture, there's your 2 orbits. They're the boundary of the annular global surface of section. They're, not the same. We could discuss why that is. But if I have any other periodic point, then I have infinitely many. So then I would have infinitely many orbits. Okay. So that's cool. I mean, you can learn about this from the HWZ paper, and it's a great idea. So that's sort of what we're going to try to do. Are there any questions about that?
Yeah. This theorem by Franks is the reason why you would choose an annular.
That is a fantastic question. So you could actually do something more general. That is the theorem by Franks, and if you have an annulus, let me just go back. If you have an annulus, then you can apply the theorem by Franks directly. On the other hand, there are other theorems you could apply. Let's say this had genus, okay? Well, okay, in principle, you could have an area preserving it's going to have 0 flux, or the flux is going to be undefined. And so you can still deal with the higher genus case that way. So in other words, if you had like any global surface of section, it turns out you could get these arguments to work. However, in our proof, it turns out to be very important to deal with annular global surfaces of section. So in other words, this part would work just as well if I had genus, but later, it's going to be very important to not have genus. So that's actually why I said that's a great question. Is right. So yeah. Does that answer your question?
Yes, absolutely. Thank you.
Okay. Yeah. More questions? I mean, like I said, with these technical things, like well, feel free to say like to go back too, because I don't want people to lose the flow of the argument. It's like a board talk, you can see like 6 blackboards at once, but we're only looking at 1 slide. So just let me know if you want me to stop or go back. Okay, so anyway, so that's sort of the goal. Okay, so how on earth are we actually going to do that? Well, there's another beautiful idea in the HWZ paper. Maybe some of you have seen it before. But yeah, it's a great idea. So HWZ tell you that you could try to search for this by finding a J-holomorphic cylinder in the R cross Y. So again, like for non-specialists, this thing is called the symplectization. J-holomorphic curve, just means du composed with little j is j composed with du. Index 2, maybe we'll get back to that in a minute. This projection, I just mean literally this manifold X just projects down to Y. So if I can find a cylinder in R cross Y, so this would be like again, if you're I mean a cylinder in the SFT sense. So if you're not a specialist, this would be like a sphere with 2 punctures. So it's some non-compact thing in R cross Y. And yeah, so maybe I can find that thing and project it to R cross Y, and that would be a global surface of section. So this is pretty cool, but you could ask like, why is this even, a good idea? I mean, I like this because, if I ask you to find a global surface of section sort of by hand using topological arguments or something, it seems like it could be pretty complicated. But this is telling you that you can sort of turn it into some kind of geometric analysis problem. And to first approximation, I'm sweeping certainly some details under the rug for expository reasons. But what you should imagine is maybe get back to this index 2 condition. So I have a cylinder that has real dimension 2. Index 2 means that my moduli space has dimension 2. So in other words, my cylinders lie in some two-dimensional family. So you want to put the equation 2 + 2 = 4 in your head. So if it's an index 2 cylinder, there's a chance that as I move in my moduli space, the cylinders sweep out, this entire 4-manifold X. And maybe they even sweep it out sort of disjointly in the sense that no two cylinders are going to intersect. Okay, I also have some control over my almost complex structure. Maybe we'll return to that in a minute. But at least you should hopefully find it plausible that I can turn this question of finding a global surface of section instead into this question about finding foliations of this 4-manifold with different J-holomorphic cylinders. So that's kind of an idea with a long history. Are there any questions about the basic idea?
No,
Okay. Oh, well, I heard a question. So why don't we go with the question first, and then I'll
no, it was my attempt to substitute vocals for the visual, because you say you don't see us. We were negatively expressing there are no questions.
Oh, okay, great. Okay, so like I said, this idea goes back to HWZ, but I want to emphasize that there are certainly a lot of rather new aspects here. Maybe the most notable is that the entire point is that I don't want to assume that the contact form is non-degenerate, but most of the J-holomorphic curve theory you learn about, at least say like in a graduate course, is in the non-degenerate case, and there are serious challenges trying to do J-holomorphic curve theory in the degenerate case with absolutely no other assumptions at all. I mean, it might, in general, it might not even, it might not be a Fredholm problem. There might not be a unique limit to these curves. I mean, in general, this could be a very messy problem. Here, it's not quite so bad because, remember, I can assume that lambda has finitely many orbits, or else I'm automatically done. So that helps somewhat, but it's still, a substantial undertaking to try to push these ideas to the degenerate case. Okay. Okay, so that's sort of something we have to do. Anyways, so if I look at the problem then from this point of view, I see that basically there's two aspects that I have to deal with, and they're actually linked. We'll talk about that in a minute. Okay, so first of all, I have to understand, in this degenerate case, how can I find some reasonable criteria so that this sort of first approximation argument I had of foliating X by J-holomorphic cylinders actually works. I'm calling that problem P1. And then I also need to show that there actually is the J-holomorphic cylinder that satisfies these criteria, which is also seems formidable because, I mean, again, a lot of the tools we have for even producing J-holomorphic curves are in the non-degenerate case. Okay, but so those are the basic problems, and they're linked, right? Because, and this certainly comes up in our paper as well, because I have a certain amount of control, right? I mean, I can try to make my criteria as strong as I can, but if I demand more and more out of my criteria, if I demand more and more out of P1, then it's going to be harder to satisfy P2. So I can play a kind of game, demanding a lot out of P1, seeing if I can get P2 to work, and if not, try to relax P1 a little bit. So, so you wouldn't want to think of these problems completely independently of each other, but those are the basic structure of the problem. Okay, so I now want to go into both P1 and P2 in more detail, but I want to see if there are any questions about any of this.
So P1, do you mean given a cylinder, how do you test to see what it projects to?
Right. Say you give me some J holomorphic cylinder in R cross Y. You know, what kind of things can I demand so that it's actually going to project to a global surface of section for the flow? This GSS, this just means global surface of section.
Can you really think of P2 independently of P1 then? Because you're saying it's satisfying, I mean, or do you mean P2 in the sense of just let's see if we can find any cylinders at all?
No, I'm saying they're linked, right? So I put the word linked. Maybe I'm not sure I completely understood the question. I put the word linked in parentheses. So I don't want to think of them exactly as independent. You know, I want to so I think this might be a little clearer too when I fill in more detail. But
Sure.
you know, I think it's good to discuss now. So if I just have like a J holomorphic cylinder in R cross Y, there's no reason to think that it would project to a global surface of section. You know, like even in my let's look at what I wrote in my first approximation here. I'm saying like basically even in first approximation, I want something like the curves. I want something like the deformations of the curve to foliate the four manifold. But if I just have a general J holomorphic cylinder, that won't be true. And even that was just a first approximation. That's sweeping some details under the rug a little bit. So I'm saying if I just have like a random J holomorphic cylinder in R cross Y, you know, there's not a lot. I'm not going to be able to get much from that. On the other hand, I could try to demand a lot of things from this cylinder. You know, maybe we'll talk more about that. But then if I demand a lot of things out of this cylinder, then the problem of actually finding such a cylinder is going to become harder. So does that sort of clarify?
Oh, but yeah, thank you. Yes.
Okay. Yeah, we can always go back to this slide too. I mean, this is a bit impressionistic because I just want to give you the kind of overview of the how to do this. So are there any questions? Any more questions by anybody? While I'm there. Okay. Okay. So let's talk more about P1. So I've reminded you what P1 is. So these should be criteria guaranteeing that a J holomorphic cylinder actually projects to a global surface of section without assuming non-degeneracy. So this looks like it could be pretty complicated, and it is pretty complicated. However, there's a really important idea. Like I said, the proof is pretty technical, but I want to try to convey what I think are the most important ideas. So here's an idea, which is, I think, very useful, maybe known to some kind of super specialist. But anyways, it says that, okay, so I don't want to assume that the contact form is non-degenerate. Remember that if I did assume it was non-degenerate, I would get a lot of the theory of J holomorphic curves from the non-degenerate case. But what does the idea say? It says that as long as the cylinder converges exponentially fast to the Reeb orbits at its ends, it still works somewhat like in the non-degenerate case. Okay, so I drew a little picture here for you, especially if you're a non-specialist. Okay, so here I have a cylinder. Remember, this cylinder is sitting in R cross Y. What gamma minus and gamma 1 are these are Reeb orbits. And so, like I said, again, the whole thing is sitting in R cross Y. So let's take, say, the negative end, the gamma minus. So when I draw a picture like this, that's saying that as I go off to negative infinity, the cylinder is actually converging to gamma minus. Like you could look at, for example, just gamma minus cross R, and point-wise, let's say the cylinder is converging to gamma minus cross R. But I'm saying that in the non-degenerate case, you actually get a lot more if you set it up correctly. Not only does it converge to gamma minus cross R, it converges exponentially fast to gamma minus cross R. That's something that you get, I'm sweeping some assumptions under the rug, but that's something that's quite standard in the non-degenerate case. And what I'm saying is that ends up being a kind of a crucial point. What we really want is we want the exponential convergence to gamma minus, even without assuming non-degeneracy. And then similarly for gamma plus, or I've drawn it as gamma 1 here. Somewhat mysterious reasons. Okay, so are there any questions about the key idea? So what I'm saying is, if the thing converged exponentially fast, then I could argue as in the non-degenerate case. Okay, so maybe I should tell you then, especially for people who aren't so used to thinking about this, is what actually works in the non-degenerate case, right? I mean, I'm saying from the previous slide that we should hope that the cylinder converges exponentially fast, and then we should try to appeal to the non-degenerate case. So what is actually true in the non-degenerate case? Like, say I have a J holomorphic cylinder from gamma plus to gamma minus, and I want it to project to a global surface of section. What is it that I need? Well, okay, so the first bullet point I put here is, well, okay, what I need is one thing. We really just want something that suffices. So what's going to suffice? Okay, so first of all, I need the cylinder to have index 2. So here by index, I mean the Fredholm index. Again, this just means that the cylinder, at least if everything is transverse, is going to live in a 2-dimensional family. Also, you know, in parentheses, I put a point that if you're a non-specialist, maybe you can just ignore or something, or, you know, if you're a specialist, you're already assuming this. I need some control over the complex structure. So the general kind of control you want, the almost complex structure, J. The general control you want is that the almost complex structure is admissible. So that means that it's going to send, you know, so these things are living in R cross Y. It's going to send the direction, the R direction, to the Reeb vector field. You know, the direction that just goes up in the R direction to the Reeb vector field, and it's going to preserve the contact structure compatibly with D lambda. So there's this admissibility condition. I want the cylinder to have index 2. Okay. Let's say I want the cylinder itself to be embedded. You know, so remember the cylinder is just a map from a twice punctured sphere into R cross Y, but I want that map to actually be an embedding. Okay. Remember, I had this criteria that I wanted the deformations of the curve to sweep out all of R cross Y. So, okay, so let's try to make that a little bit more precise. So I can look at the moduli space of all J holomorphic curves, and I can look at just the component of the moduli space containing C. Okay, so I just look at the curves in the same moduli space component, and I'd like that to be compact. Okay, well, it can't be compact because, well, in this admissibility condition, I want my almost complex structure to be R invariant. And so there's a translation action on this moduli space. But okay, but modulo translation, I want this moduli space to be compact. Okay, so there's 2 more criteria, but are there any questions about the meaning of the first 3 criteria? I especially mean for kind of whatever non-specialists are here. I mean, you know, well, yeah, anybody really. But what I mean by these terms, like the index, etc. Okay, I don't hear any questions, so maybe I can continue. Okay, so now there's actually other criteria. It turns out to be useful. So remember, my cylinder goes from one orbit to another. Turns out to be important that the orbits have odd Conley-Zender index, or at least useful that the orbits have odd Conley-Zender index. And there's even a stranger condition that, you know, unless you're sort of like really immersed in this kind of theory, you might never guess that this is an important condition. So let's talk about it, because it's sort of a fun condition and not unrelated to how the proof actually works. But you know, if you're not that into this kind of stuff, you can just tune out for the discussion of 5, because it's, you know, it's really getting into the details. Okay, so okay, but I do want to talk about 5 a little bit. This cylinder, it goes from gamma plus to gamma minus. These are Reeb orbits. Okay, so gamma plus, you know, it's going to be a cover of some simple Reeb orbit. right? Just because it's an orbit. So I'm saying you could look at some underlying orbit and then go around it m times, and there is going to be some m such that it's an m-fold cover of that. Meanwhile, the simple orbit has a so-called rotation number. I didn't put the definition of the rotation number on the slide because you could sort of guess what the rotation number should be, at least more or less. But the rotation number is just telling you about the local flow. Roughly speaking, the rotation number measures the rotation of the local Reeb flow near gamma plus. So it turns out anyways that if I take the greatest common divisor of m and the floor function of m times theta, I need that to be 1, which may or may not happen. I mean, this rotation number, since this is non-degenerate, this rotation number is going to just be some irrational number. M is going to be some number, and then you can just compute, and maybe it'll be 1, maybe it won't. But we really want it to be 1. Okay, so that's pretty fun. I like that. Okay, so let me try to give you some idea. So I'm saying that if you have a J-holomorphic cylinder and it satisfies these 5 criteria, it's going to project to a global surface of section in the non-degenerate case. And I guess, again, to put this in some context, I want to say that, by now this kind of thing is well known. I mean, these ideas themselves go back to HWZ and then were further developed by many people, Wendell, lots of people. In this current form, I think this particular proposition is due to earlier work of myself and Michael and Dan Pomerlano. But at any rate, this is a kind of known thing, but it's a beautiful idea. So let me sort of give at least a general sense of why these criteria are important. Basically, what 1 plus 3 are guaranteeing you are sort of the kind of thing that I was saying before. So I have a 2-dimensional family of real 2-dimensional objects. It's going to move around in this 4-manifold, and roughly speaking, as long as this moduli space is compact, it's gonna at least make it to the whole manifold. Okay. Now remember, I said I actually want it to be a foliation. So that means that I want the 2 different curves, different curves, 2 different curves. I want them to be disjoint, right? For it to be a foliation. Yeah, so this is pretty cool. That's sort of what 2 and 4 are buying you. I didn't put it on the slide, but maybe I'll say a few words about it. Again, there's sort of a picture you should have in your head, which is like, I just have 2 different curves. Again, stop me if I'm going too fast or something, or you want me to draw a picture or something. But anyways, I have 2 different cylinders, and I'd like them to be disjoint. Okay, so obviously I can try to do this with some sort of intersection theory, but I need to do some kind of asymptotic intersection theory because the curves are not, closed. The cylinders are not closed. They're all asymptotic even to the same Reeb orbit. So I need to do some kind of asymptotic intersection theory. It's still not entirely clear why 2 and 4 are exactly what are needed for that. But basically, maybe the first case I could try to do is I could take my cylinder and I could imagine translating it a little bit in the R direction. And, maybe I'd like at least that to be disjoint from its translet. And infinitesimally, whether its disjoint is controlled by the so-called normal Chern number. So there's a sort of expression in terms of things like the Chern class, etc., Chern classes, etc., measuring infinitesimally whether a curve is disjoint from its translet. And anyways, if you work it out, it turns out that the parity of the Conley-Zender index is important in bounding this normal Chern number. So basically, you'd like it to be 0. So if you can just bound it by something which is 0, you're in good shape. And if the orbits have odd Conley-Zender index, it turns out that really helps. And then once you're disjoint from an infinitesimal translet, you can upgrade this to being disjoint from a general translet. And now you have 2 different curves in this moduli space, namely that are disjoint. And okay, I mean, then you can argue that any two curves are disjoint by comparing to C and its translate. Pretty cool. Okay, as for 5, basically what that's doing is it's controlling the return time near the boundary. So remember, like what we really want, the picture that we want is that this curve is going to project to something that's transverse to the Reeb vector field, and then we want to do this. We want to follow the Reeb vector field to get this return map. And okay, if I go closer and closer to the kind of the boundary of my projected cylinder, maybe I'm still transverse to the Reeb vector field, but I need to understand how long it's going to take to come back. I want that to be like some finite number. And it turns out that if you have this nice condition on the rotation number, that'll get the job done. Okay, so those are 5 criteria, more or less well known, for a J-holomorphic cylinder in the non-degenerate case to project to a global surface of section. Are there any questions about that? Okay. Okay. So, for time reasons, I'm going to be a bit impressionistic with the rest of P1. But so now what I'm saying is, under the condition of exponential convergence, I need to find analogs of those criteria. And so, the basic idea is actually that this is not so hard, at least more or less, as long as you have the exponential convergence, because you can use a rather well-known technique called exponentially weighted Sobolev spaces. So if I actually have exponential convergence, even if my contact form is degenerate, I can set up. I still get a Fredholm problem, but by building exponential weights into my Sobolev space, and then I still get a Conley-Zender index, so I can make sense of the Conley-Zender index being odd, and I still get even a notion of automatic transversality that actually holds, for the right criteria. So just like going back slightly, if you look at what the 5 criteria are, I mean, if I have an index, I can still make sense of criteria 1. Criteria 2 doesn't, that certainly still makes sense in the degenerate case, as does criteria 3. Odd Conley-Zender index. Okay, now I do have some weighted Conley-Zender index, and you can make sense of 5 as well. So I don't want to say much more here because I want to leave a little bit of time to say a bit about how idea P2 goes. Are there any questions about idea P1 though?
Do you commonly expect to encounter exponential convergence?
Yeah, great question. That's the key question. Exactly. Yeah, so we'll get to that in P2. So maybe I'll just go ahead to P2 because that's like definitely the crux of the issue. Right, and that's sort of what I mean by the two things are related. Like in P1, you can demand exponential convergence, but then you're left with a quite hard problem in P2, which is you want to show that a J-holomorphic cylinder satisfying these criteria actually exists. So to link to your question, Sarah, yeah, so I can demand exponential convergence in my moduli space, but then I have to show that that moduli space is not empty. And so I have to know that I actually have a cylinder using exponential convergence. And that's kind of, in my opinion, what's the miracle of how it all works, actually. I mean, that's like what I consider the most cool feature of why it actually works. Okay, so this gets quite involved, but I want to at least give you an outline of the argument. Okay, so I want to just find some J-holomorphic cylinder for lambda, so I can approximate it by non-degenerate contact forms, lambda n. And for each of the non-degenerate ones, I can use the full force of floor theory to find these J-holomorphic cylinders. In particular, I can use so-called embedded contact homology. We'll say a little bit about embedded contact homology on the next slide. And then I can find the desired cylinder by taking some kind of limit. So in other words, to put this in some perspective, I'm just saying I need to find a cylinder, just like Sarah was saying, with exponential convergence at its ends. And I'm going to attempt to do this by approximating my contact form, finding J holomorphic cylinders for each of the approximating sequences, and then taking a limit. And just like Sarah was saying, this is only going to work if we're extremely lucky, because remember, I was saying it's pretty standard in the non-degenerate case that you have exponential convergence to, to the ends of the curve. But you could certainly imagine that the decay rate of the CNs is tending to 0. So, I want to pause because I consider this really like a crucial point in the proof. I mean, in other words, certainly each CN, it's not hard to guarantee that that's going to be converging exponentially fast to a Reeb orbit at its ends, but the speed at which it's converging could be going to 0. And then, I could definitely be losing exponential convergence in the limit, just like Sarah was worried about. And so that's a key problem that we definitely need to address. Are there any questions about the scheme or the crucial point? Okay, so let's at least try to sort of say how this goes. So like I said, we want to use this embedded contact homology. There have been many, many talks on embedded contact homology, so I don't want to belabor this too much. The homology of a chain complex requires the contact form is non-degenerate. It's generated by sets of orbits. The differential counts ECH index 1 holomorphic curves in R cross Y. The point is that this index 1 condition, for the most part, forces the curves to be embedded. That's why it's called embedded contact homology. And very importantly, it's isomorphic to the Seiberg-Witten floor homology. So it's very, very non-trivial. That's already important for our purposes because we want to find some holomorphic curves. If this thing is 0, it's not going to be very useful for that. It's isomorphic to the Seiberg-Witten, so it's not 0. Okay, I went through that fast because many talks on ECH theory. We need 2 facts that are more subtle. I call them F1 and F2. The first is, remember, we actually want index 2 curves. So there's a map on ECH. It decreases the grading by 2 called the U map. Taubes' isomorphism is telling you that it's quite non-trivial. That's something you learn from Taubes' isomorphism. So in fact, for any power, it's non-trivial. The other thing, and this is getting sort of close to where I want to stop. I guess I want to take an additional 2 minutes because I had some technical difficulties. Whatever. Anyways, the other thing which is a bit subtle are these so-called partition conditions. I think it's actually easiest to illustrate this with a picture, but it says that the ends of the UMAP curves are determined combinatorially by this rotation number that I was talking about earlier. So maybe I'll just go directly to a picture. Okay, so here's a particular UMAP curve. You already learn a lot of interesting things about this. It could have genus, it could have many punctures, whatever. What are the partition conditions saying? Well, I showed you this chart, which is a bit small, but it says that the partition conditions tell me what is the combinatorics of the ends at a particular orbit. Like for the picture that I drew, say that I have say that all 3 of these blue ends are at the same orbit. So in this case, I would have like 3 different ends of my curves. Let's say they're all even at a simple orbit. What the partition conditions are telling you is that if this is a UMAP curve, this can only happen if the rotation number for that orbit is of a very specific form. This is somewhat analogous to that strange condition 5 I gave about the greatest common divisor of M and the floor function of M theta. And this chart over here from Hutchings's book actually tells you how this combinatorics goes. So this is just a chart where it tells you how to, it says that if you're an ECH curve, on the left-hand side, you get the rotation number, and on the right-hand side, you get the combinatorics of how the ends look. Okay, so that turns out to be very important in the proof. Okay, so, we don't really have time to go into, much, but let's just sort of close by saying the key ideas. Maybe I want to skip over this a little bit and just sort of get to the the key point. So there's various things on the slide, but I just want to highlight this key point. So what you do is you use this U map. In fact, you use the U to the N map to get a lot of holomorphic curves. Really the key new idea is that you can actually show that most of these curves are cylinders, which is not at all obvious because even in the picture that I gave, there's no a priori bound on the topology of ECH curves. And we define a new invariant for these purposes. Okay, so nevertheless, you use the U map, you get a whole pile of J holomorphic cylinders. And then it turns out that this exponential convergence issue takes care of itself once you have the cylinders. So, I'll stop pretty much here. But so you have this rate of convergence, you have to bound it away from 0. But the point is that it is known how this rate of convergence actually works. And it's related to the rotation number. And then that rotation number itself is determined by the partition conditions. So if you work through it all, what you need that the cylinders Cn are asymptotic to curves with say slightly negative rotation number, at least in this special case. Okay, so that was pretty fast, but it's really important to have cylinders for this. Another important idea is that the cylinders need to have small area. They need this integral of the contact form to be small. So it just turns out kind of by magic that if you have small area cylinders, the asymptotic analysis plus the partition conditions is taking care of this exponential convergence idea by itself. So I think that's a good place to stop. I had some open questions, but there is a question and answer time. So I think I'd rather just stop and then happy to talk about things more in the question and answer time.
Okay, great. Let's thank Don for that. Any questions?
Could you at least briefly address this mysterious spore invariant?
I'm sorry, could you repeat the question? I couldn't quite hear.
Could you at least give a sense of what the spore is?
The score. Yeah, sure. That's actually the bonus slide. Okay. So, right. So to put this in this context, we have these ECH UMAP curves, and we need to control their topology. In particular, we want most of them to be cylinders. I made a slide about this in case someone asked. I guess I'll go through this. I'm going to answer your question, but I'm going to take a couple minutes to answer it so that I can answer it somewhat properly. Okay, so the score is supposed to help with the following problem. How do I show that these curves are cylinders? So the basic idea is, like I was saying before, you have this U map. It counts index 2 curves. So I actually want to look at the U to the N map. The basic reason for this is that the philosophy is that if I just look at a random UMAP curve, hard to control much of it. So instead, I want to use some kind of probabilistic argument about N curves in a row. So you get these like N curves from the U to the N map. They're in a row in the sense that, like, say the negative asymptotics of C1 are the same as the positive asymptotics of C2, etc. And just because the UMAP is counting index 2 curves, I know that the total ECH index of the N curves is 2N. And now the next important part of the background is that there's another index, this so-called J0 index. This is the only place in the entire proof where the assumption that the Chern class is torsion is actually used. So it turns out, and again, there's kind of a history of ideas about this, that this J0 index is approximately the ECH index. And so what you get is that, what you get from step 1 through step 4 is that most of the curves have J0, let's say approximately 2. Okay, now what is this J naught index? I didn't exactly say what it is. It's a variant of the ECH index, but let me highlight the formula. So this is the kind of key point. So basically, well, J naught is -2 plus twice the genus of the curve, plus a certain measurement of the ends. And so you should be thinking from step 1 through step 4 that the curves have J naught about 2. And so we want them to be cylinders. Okay, so if it was a cylinder, then this genus term would vanish, and then this E term, this measurement of the combinatorics of the end, would be 4. So that's the kind of thing that we actually want. But there are other ways J naught could be 2. Like the G term could be 1, this E term could be 2. By the G term, I mean the genus could be 1, the E term could be 2. Right. So that's the formula you have to stare at. In order to motivate the definition of the score, you really actually do have to understand what this measurement of the ends is. So I wrote what the measurement is. It's a little hard to digest in real time, but okay, so this decomposition of the curve into C0 and C1, we could go back and look at my picture of the UMAP curve, but if you remember the ECH curves, they could have multiple components. It turns out that they have only one sort of interesting component, that's the C1, and everything else has to be R invariant. And that's actually important for understanding what the score is doing. So you look at the interesting component, and you look at the number of ends that it has at each orbit, and then you also have to look at whether there's an R invariant cylinder at that orbit. Similarly, you do the same for all the negative ends, and you add it up. So the basic point, if you look at this E thing, it's going to get bigger and bigger as you have more and more ends. So if J naught is about 2, you would like that you have exactly 2 ends. The genus is 0, and if you stare at the formula, the way that it's going to work is going to require that you have trivial cylinders, R invariant cylinders. This C0 thing is supposed to be an R invariant cylinder at each end. However, there are other things that could happen, like the genus could be 1, and then you could have no trivial cylinders at all, and the E term could be 2. So the score is defined precisely to force the existence of trivial cylinders. So I guess the basic principle, if you stare at this for a while, and again, it's kind of hard to absorb this on the fly. I mean, it took like quite a lot of staring at formulas to cook up this score. But the basic principle is that your UMAP curve has R invariant components and not an R invariant components, and if and a single non-R invariant component. And if J naught is 2, you would like there to be R invariant components. So the score is supposed to penalize you for the failure of these R invariant components to exist. So I could write a formula, but I think it's not going to be that useful. Better is to say the principle, which is just that you want to exploit the partition conditions. So basically, if you remember that chart, I was saying that the ECH curves are subject to like quite severe restrictions on what the combinatorics of their asymptotics can look like. If you have these trivial cylinders around, it gives you a little bit more flexibility. And so the idea is you want to force the existence of trivial cylinders by penalizing you for having to satisfy the partition conditions on the nodes. So it's a bit complicated, but it really uses the fact that these n curves are in a row. The negative asymptotics of one are the positive asymptotics of the other. I wish I could give a better sense for it, but I mean, to sum up, what you want is you want C1 to be a cylinder, and you want C0 to just be a union of 2 R invariant cylinders. And that should have score 0. And when I say the score is supposed to penalize things, the score needs to have the property that all the other possible ways for J naught to be 2 should have positive score. And that allows you to turn this problem of finding cylinders into a problem of bounding the score. And then there's this ECH while law, which you can use to bound the score. it's quite a complicated story. But anyways, that's the, maybe at least I convinced you that it's a complicated story.
Oh, certainly, yes. But also apparently quite cool.
Any other quick questions before we stop recording?
Yes, I have. Hi, Dan. I have a quick question.
Oh, sure.
I had the impression, but it's probably naive, that at some point you said that if a cylinder is asymptotic to an orbit with a given rotation number, then you can somehow predict the asymptotic speed of convergence.
Well, I didn't quite say, yeah, let me go to the
No, you
relevant
didn't
slide.
say that.
I went through it pretty fast. I said that, I think you're talking about this slide. So I said that there is a relation. I said that there is a relation
Yes.
between the rotation number and the speed of convergence.
Yes.
And I went through this pretty fast. So it's a little bit weaker than saying, you know, you can predict it. So what I'm referring to here, if I wanted to talk more in specialized terms, you know, I'm just referring to the asymptotic analysis, you know, kind of package where you relate eigenvalues of the asymptotic operator to the Conley-Zender index, let's say. So you know
But this is a general fact. It has nothing to do that you have the U map.
Right, that's right. All of this is general. The only part where you're using the U map is this third bullet point about the partition conditions, or maybe it's really, yeah. So let me actually say this a little bit more slowly. But right, so there's just general stuff. And then I'm saying, okay, so the heart of the issue is to, because we're interested in the degenerate case, the heart of the issue is to understand what's going on, say if the rotation numbers are going to 0, then you use the general stuff. And if you work through it, I mean, I just want to say it because it's pretty cool. The heart of the issue is that this is, you want to understand what's happening if this goes to 0. And if you work through it, I mean, there's only 2 ways the rotation numbers could be going to 0. They could be getting slightly negative, or they could be getting slightly positive. And it makes a huge difference if you work through the asymptotic analysis, whether they're slightly negative or slightly positive. And the partition conditions save you because it turns out you need to know that the rotation numbers are slightly negative, and that exactly follows from Hutchings's chart if you look at the chart. So so it's actually not such a complicated thing. It's just a funny fact that it makes a huge difference if the rotation numbers are slightly negative or slightly positive.
Okay, thanks. And maybe one more question. Why do you want the areas to be small, the integral of over Cn of d lambda n?
Yeah, right. I also did that rather quickly. So there's 2 reasons for that. One reason is that if you look at this table, the partition conditions only become, you know, interesting. It's sort of obvious that they can only become interesting. The partition conditions can only even be useful if I am at an m-fold cover of a simple orbit where m is at least relatively large. I mean, in other words, if my cylinder just has simple asymptotics, then you know, I'm obviously not going to be able to extract anything from the partition conditions because the partition is just going to be 1, you know, by fiat. I only get something interesting if the cylinder is asymptotic to an m-fold cover for m rather large. So if the d lambda area is small and there's only finitely many orbits, it's a little complicated because, okay, the lambda n's are close to a contact form with finitely many orbits, which is does not guarantee that there's finitely many orbits. But okay, as a warm-up case, you can imagine that if the d lambda area is small and there are finitely many orbits and you have a cylinder, then it has to, the asymptotics have to be winding around the Reeb orbit lots and lots of times. Do you see what I mean? Because you only have finitely many orbits. So in order to have, you know, like if you're just asymptotic to simple orbits and you only have finitely many simple orbits, you're not going to be able to produce small d lambda energy, you know, ever. So in other words, if you have small d lambda energy, you have to be picking up high multiples of your asymptotics. And that's really important if you want to extract anything from the partition conditions. That's reason 1 why it's useful. The other reason is this compactness. You know, if you looked at P3, I want the component of the moduli space to be compact. So if I have a general cylinder, it's quite hard to show that that's compact. But if it has small d lambda energy, you have much more control over the breakings. Like, for example, in general, you could imagine bubbling off like a disk or something, breaking along a disk. But as long as the action is smaller than the systole, you can't give birth to a disk. So the small action really helps with P3.
Okay, thanks very much.
And I mean, I think you know this, but the small action is a consequence of this ECHY law. It's not kind of obvious that such curves do exist, but it's well known by this point. Well known before our paper that this is a kind of well-known thing in the ECH community these days. The low action part.
Very good. Well, let's thank Dan one last time, I guess.